All right, good morning. So we're gonna today's last class of the semester. So thanks for your attendance, your patience, engagement in the class. I hope it's been at least a bit interesting and informative. I hope you've felt like the MATLAB and this related stuff has been useful, and hope you find that to not be too frustrating over the next week as you accomplish your projects. Please do be in touch with me about those as you go if there's any need. You're also welcome to write a little side note with your assignment to say, hey, this is what I felt about this. This part was too much. This part was a lot easier than I thought. Whatever feedback you'd have, I'd really appreciate it. Just to know like kind of how that experience was for you for next time I teach. Actually, and I'm going to teach an undergraduate version of it next semester. And there's a couple students that wanted to do the honors version. I'm like, okay, well, just make them do what you guys just did for that. So my current plan is to give them a slower, easier time with the MATLAB, and hopefully a little more consistently, like do this little step. So would just love your feedback there. You're also welcome and highly encouraged to give me feedback and the university feedback through the evaluation system. Welcome to be, so it's anonymous. Of course, there's only 7 of you, so don't make it too obvious if you want to be anonymous. But regardless, I read all of those for this class as well, and kind of especially because it's my first time teaching it. So love the feedback there also, and give me whatever evaluation you think is appropriate. Right? I know it's not going to sink me if you're like, yeah, you're a little disorganized because it's your first time teaching this or whatever. It's no problem, right? So whatever you feel is appropriate will be good. I just would be happy to see that it's not just like one person that filled out some feedback. That's a little worse than like, because that could skew it. But anyway, today I was going to talk a little more about photochemistry. We'll see how far we get and maybe see how interested we are. I could probably talk your ear off, like I said last time, ad nauseum. So maybe we don't want to spend the full hour and 20 minutes today because it's the last day. I don't know. So we'll see how far we get. But before that, I wanted to go through the exam. I haven't graded them yet, but I've prepared the solution. So I want to talk you through that just so you can kind of know what to expect now. I probably will have them graded in the by early next week, so I can get that out of the way before finals and final projects. Okay, so first 3 problems were true or false. First one is corrosion control could have prevented the lead exposure during the Flint water crisis. I would mark this as true. That was almost entirely the reason is because the water, the Flint River water was much more corrosive than the water that had been coming from the Detroit water treatment plant, which I think they were at least evaluating, if not adding corrosion control, evaluate it for corrosivity. So that change was what started leaching lead particles off of the pipes, and you start getting metal and lead in that coming into solution and exposing people drinking the water to lead. How many of you, just out of curiosity, watched and enjoyed one of those lectures, or what's the lecture, right? So some of you maybe were like, oh yeah, I forgot. Hopefully you found that useful. Did I also give you guys the readings to look at, or did I skip that? Okay, I gave my other class a little task to read some. You nodding yes, maybe I gave some reading. The video, yeah, okay. There's a couple nice papers on it. I didn't really feel like you needed to go to that level to at least get this to answer this one. So clearly I wasn't, really like you must know all of this, but there's a couple good scientific papers about what was going on with it as well. So if you're curious, I'm happy to share. If I think of it, I'll probably post them to Moodle just as a little supplement. Okay, number 2, true or false. EDTA, which we talked a fair bit about, titration for calcium determination performs well at neutral pHs. that is false, because while it does technically perform, if we think back on as we change pH, our EDTA has like all sorts of pKa's, lots of them, and calcium kind of is not chelated, but is compounded strongly by the upper ones, the Y3 minus and the Y4 minus. So it works really well at basic pHs, and it still functions, it still happens at a neutral pH, but it's not really enough to actually see a big difference in practice, because as soon as you add just a tiny, tiny, tiny bit of base, it's a huge difference, and so it's not very useful in terms of finding the exact amount you have to add. So that one's false there. Okay, next one, chelating agents with 5 bonding sites have a higher affinity than monodentate ligands. This one is true. So these chelating agents yeah, chelating was the right word, the claw agents, right? If they have lots of bonding sites, if you go way too much, it kind of starts diminishing, but up to 4 or 5, that's kind of the strongest you can get. It really captures your metal, and a single one attaching tends to be a lot weaker in that sense. Okay, problem 4, I tasked you to arrange these in order of redox potential, marking 1 as the most oxidizing and 4 as the most reducing. And I know that I told you before the exam that you wouldn't have much on redox, and what I was meaning to convey was I wouldn't make you do calculations. I was hoping that with the homework and with a bit of discussion that the first lecture, that something like this you could at least figure a way to approach. So we did talk about the fact that we define hydrogen as the 0 point. So that one's going to be kind of probably in the middle if we have to guess. I think I might have talked a little bit about fluorine. We definitely talked about oxygen, and we definitely talked about electronegativity and the importance there. So fluorine would be the very most oxidizing. And I think I probably mentioned it in the context of the chemistry videos that I showed you, but also the XKCD comics. I don't know if I've told you about those. I think at least these are great, kind of academic, funny web comic sort of things. And I think they're making some videos with them now too. But there's one on a pressure cooker, and it's like asking what is the worst thing you could do with a pressure cooker, and making essentially hydrogen peroxide, except not hydrogen peroxide. If you change these with fluorine gas or fluorine atoms, you get FOOF, which is extraordinarily oxidizing and will just kind of disintegrate almost anything, or oxidize just about anything. So you can't really make it and keep it stable under almost any normal circumstances. So we might have to go look at a video of kind of doing just that. There's like 1 or 2 labs that handle that stuff or similar. So anyway, fluorine is, as a gas, it's extremely oxidizing. It's the most electronegative atom that we have. So F2 then is quite. All right, so then if we look at the other 2, we know hydrogen should be probably 0, and metals, often when we dissolve them, they end up with some sort of a plus charge, right? So they're kind of electrogiving instead of electronegative or electropositive. So they kind of want to give away electrons. So this is probably, we ought to put at the bottom. And then oxygen then is going to be oxidizing as in the name. It's kind of named for that. So O2 would be the next logical one, with H2 being the middle point. So that was kind of my hope, so you would get something similar to that. I don't know. How'd you feel? Some of it, maybe? Maybe not? Okay. Yeah, so that was, you know, you'd probably, if you had no prior impressions, you'd probably have to rely on remembering specifically electronegativity affects that. But so oxidizing is that desire to pull away electrons from something else. So that's how it connects into the electronegativity, because if it's greedy for electrons, it's going to be really strongly oxidizing. Okay. Given that it doesn't seem like I equipped you very well for that one, we'll probably be pretty lenient. Okay. Number 5, how do you calculate the pH of a saturated solution of silver hydroxide with a solubility constant here? Now this was, we might think of a more complicated situation where this could be a more difficult problem. But if this is all we know, then really what we're looking for is to find H+, and that's going to be fairly direct because we can find an OH- value and then use the solubility product of water. We know that's going to be OH- times H+. Right? So if that's the case, then we can, if we find OH-, then we can find H+. So that means we need to find OH-, and we have another equation here where we can say this solid will be in equilibrium with silver plus and OH-. This is dictated by the solubility product. That was 2 times 10 to the minus 8. So we should set that equal to Ag plus times OH-. We could add in the solid on the bottom there, but the solid, by definition, that's going to be 1, so it would be divided by 1. Okay, so that gives us a way to find OH-, but we still have the unknown of Ag+. So what we can do here is simply say we're not given any other information about anything else in solution. So if we're saturated, that means, well, the only real source of silver is probably also really the only source of OH-. And then we'll let water do its thing with equilibrium. So what we can say then is OH- should be the same as Ag+, and that means we can solve for OH-. Because we can substitute it in and say that's OH- squared is equal to 2 times 10 to the minus 8. We do that math. OH- should be 1.41 times 10 to the minus 4th moles per liter. And we can come back up and find H+ so that we can get pH. So H+ should be 7.07 times 10 to the minus 11 moles per liter. That means our pH is 10.15. Okay, makes sense? Next one's pretty similar. How do you calculate the maximum concentration of Mg2+ that could exist in a pH 8.5 solution before precipitation of magnesium hydroxide solids begin to occur? We have a solubility product, 5.61 times 10 to the minus 12. So basically we have to just calculate the saturation condition, or rather calculate the magnesium 2+ for the saturation. And I suppose if we want to be really picky, we then subtract 0.00 something 1 just to say just under it. But we'll just calculate it at that condition. That's the max that would be there prior to precipitation. So looking for some magnesium concentration here. We know we have pH 8.5. That means our H+ simply 10 to the minus 8.5. We can then calculate, before we even really need to know anything where we're going, we probably need OH minus, so we can go and calculate that based on the, again, K for water is 10 to the minus 14. So this should be 3.16 times 10 to the minus 6 moles per liter. Okay, so then what we need to do is set up our solubility product equation. This is 5.61 times 10 to the minus 12th. And we can set that equal to, just like we did last time, the products over the reactants. Now, in this case, we have magnesium 2+, and then we have 2 hydroxides. So the way we have to handle that is to put OH minus and square it, again, over 1 here. So the squaring it here is the potential miss that you might make if you forgot how to deal with that. Okay, so with that we can solve for the Mg2+ concentration, given that we know the hydroxide. So under these conditions where we are at the solubility, which is really technically the max before we get anything forming, we can say this is going to be equal to Ksp divided by the OH minus squared. So put in those numbers and we should get 0.561 moles per liter. Okay, does that make sense? So not overly complicated, but not entirely trivial either. All right, problem 7. We had a chart to create, or a graph to create. It says if the solubility product for Ksp for calcium sulfate is 10 to the minus 4.36, sketch a solubility diagram on the space below showing the region where the solid will precipitate. So we looked at some things like this with I think, calcium carbonate, and we looked at that with an open and a closed solution. And in I think it was the closed solution in that case was a little more complicated because we were going to be going through different types of carbonate. Whereas the open solution will just have the total carbonate will change with changing pH, because and then it's a little more straightforward, and we had kind of a straight line. This system doesn't matter if it's closed or open. We're not dealing with carbonate, said nothing about it, so it's going to be a simpler version of that. So what we need is some relationship between calcium and sulfate, and then you'll notice what we have on the y and the x. These are log scale plots, so we could simply write this as log on each of them, but because we've scaled it to log, it doesn't really matter. It's the way it will show up is log, right? So didn't mean to add any confusion there, but it's essentially a log C plot. Okay. Okay. So the way to get there is, again, to start with our solubility product, 10 to the minus 4.36, and set that up to say our solids exist in equilibrium with the calcium and the sulfate. It's pretty obvious to write it that way. I mean, I guess if we're writing the equilibrium, we need to do a plus, not this way. And of course, we can then write it like this also. Okay, from here, what we want to do is simply, if calcium is our y-axis and sulfate is our x-axis, let's set it up into a y equals mx plus b type of thing, right? So we can just kind of say yx equals 10 to the minus 4.36, and then say y equals 10 to the minus 4.36 over x. It's kind of the way to think about that. So we will say then calcium is like so. And here's where it helps and is quite convenient to transform this into a log. So if we take the log of both sides, we end up with log of calcium is equal to, now the rules for a log, when you have log of A divided by B, that's the same thing as saying log of A minus the log of B. And that comes out of the -1, and the exponent can do that little fancy trick for us. So we can rewrite this then as the log of -4.36 minus the log of sulfate concentration. All right, so that gives us a, oh, excuse me, I should have said log of 10 to that, which, because it's 10 to that, it will kind of come out. So basically that's going to equal -4.36 minus log of our sulfate. Okay, from here, now we have our plot almost ready, basically. So y equals b minus or plus mx, right? Where the m is the -1, so the slope is -1 here. So we should have a -1 slope, and we can solve for our x and y intercepts and draw a line through them, okay? So if we set y to 0, then b will have to, you would have to add log of sulfate to the left side, and then that's log of sulfate equals -4.36. So we can go down to 10 to the minus 4.36, something like here. But that's when our calcium is 0, and on the y-axis, if we look over there, calcium is 0 when that's up here, right? So we're going to start there, and then we'll do the same thing. And it turns out if we say, well, let's set this piece equal to 0, then the calcium is equal to -4. The log of calcium is equal to -4.36. So do the same thing. When sulfate is 0, that's all the way on the right, and it just becomes very simply that 4.36 on either side. We draw a line. So here's our solid. Okay, does it make sense? All right.
How are you going to mark this question? Because what I remember I did was I just found the concentrations and draw a line. I knew the line would be like that.
Yeah. So, I mean, if you got a line that looks about like that, that's good news. Okay. So not quite the intercept there. I always grade based on how apparent it is you learn kind of what this is about and how maybe to approach it. So even if you get part of that wrong, but you showed me that you were taking an approach that could maybe get you there or got you pretty close, that's pretty good. So I haven't decided on it exact numerically what everything's worth or anything like that, but you could certainly solve for different points on that line potentially just based on the solubility, right? Make a guess and see, okay, what's the concentration there? And that would be a fine way to do it. Okay, last problem. I made a couple mistakes. So on your exam, I did not put this. There are several variants of several lead oxidation states. So I'm going to grade this one based on whatever you gave me. You should be able to make a balance. I'm going to solve it for a 2+. It's a common one. It certainly is no problem. Whatever you chose. technically, we might look and say, well, the PbO2, each of the O's should be a -2, so this has to be +4. And we are using it as an oxidation agent, so essentially the Pb should be going downward. So if you chose something higher than 4, that really wouldn't make too much sense, but even still, I didn't specify, so I'm not going to be too hard on you. But hopefully you chose 2 or 1 or 0 or something, so that it makes sense. So I'm going to solve it briefly with that. Before I move on, I also made a typo on this one, and I had left a 4 here. I think one of you even maybe asked me about that, and I don't think S4 or O4 is a thing, and at least not in the 2- state. And if you do that math, the four oxygens here, each with a 2-, that means, like with sulfate, SO4 2-, the sulfur is in a +6 state, right? Because it has to account for 6 of those charges. Otherwise, it would be in the 8-. If we had a 4 here and then it was still going to 2-, that's another problem and would be troublesome. So you're getting full credit for this one. Just whatever you did, I apologize for the confusion. My bad. So I can solve it and show it to you if we care, but I think I'll focus on 1 and 3 and just maybe write up the sulfate answer for that. Okay, so we're oxidizing manganese from 2+ to MnO4- by this lead oxide. So we need basically 2, and I also should have given you more room on your paper too, so sorry for that. So we need to get 2 redox equations, and we always start with the oxidized form on the left. So we'll start with MnO4-. We generally will have to add at least electrons, if not protons as well. That'll be in equilibrium with the other form of it, Mn2+. So the Mn's balance. Now we need to balance the oxygens. We're going to use water, so 4H2O. Now we need to balance the hydrogen, so we've got 8 over here, and then balance the charges with electrons. So for the first half reaction, this becomes, where am I at? 5 electrons, right? So 8 minus 5, that's a, did I do that right? Yeah, that gives us 8 minus 6 gives us a +2 net charge, and there's a +2 net charge on both sides then. Okay, so that one's fine. We might have to revise it a little to combine everything, but next up we get our lead oxide that's going to do our oxidation. That's going to be in equilibrium with whichever lead form you chose. Yeah, just get rid of whatever I just did. And we have to add a couple waters here, get the oxygens to balance. That means we end up needing 4H+, and we'll need 2 electrons there to counteract the charges to get it to a +2 on both sides. Okay, and if we take a look, we are converting in the manganese side, MnO4 has a 1- charge, so that means manganese itself is a +7 charge. And it's going to a +2 charge. That's a difference of 5. That matches with the 5 electrons, so we're good. And the lead, if we're going from a +4 to a +2, that's a 2 electron change, and we have 2 electrons there, so we're good on that also. All right, so those are our 2 equations, but now when we combine them, we need to get the same number of electrons. So we're going to have to multiply everything here by 5 and everything on top by 2. That'll just balance the electrons so that we can merge the equations. From there, we arrange as needed. The simple way to think about it is we're just going to flip and add based on making sure there's electrons on both sides of the equation. And also such that it matches the description of the reaction. So oxidation of Mn2+ to something else. So that means the thing that's going to react is on the reactants side, and then the end product is on the product side. So as long as those pieces make sense together, so we say Mn is going to be on the Mn2+ is going to be on the left with PbO2 because that's the thing that's doing it, and everything else on the right. As long as we flip it so that those core components are there, everything will add up just fine. So we end up with 5 PbO2 plus 2 Mn2+ plus 4H+. We also have to make sure that we have no electrons remaining in solution. If we get there, one thing about the photochemistry stuff is technically we can form hydrated electrons. They're short-lived, they're basically a radical in water. So in an overall balance, we never describe them being there or a part of stuff. But in some situations, maybe it makes sense to consider them, even if they're only there for nanoseconds or less. Okay, at any rate, on the right side, we have 2 MnO4 minus plus 5 Pb2+ and 2 waters. Okay. So that would be our balanced reaction. Make sense? Okay. So if I didn't botch this one for you, and we were oxidizing thiosulfate to sulfate, that's thiosulfate is S2O3 2-. Then this should end up, and that can be done by oxygen, this should look like the final reaction would be S2O3 2- plus 2 oxygens and water, going to 2 sulfates and 2 protons. Okay. Ironically, that would have been the easiest one if I didn't make it kind of impossible. Now, the impossible part of it would be, and I didn't quite get there in my explanation, the oxidation state of sulfur in this compound, if as written in the exam, S4O4, would have to be a fraction, and we can't get a fraction, right? So you probably found that and were frustrated by that, and I'm sorry. So you were right to be frustrated and like, what the heck's going on? Okay. Oxidation of HS- to sulfate by chlorine dioxide. This one was also required some exponents that were a little annoying, some large numbers actually. So here we'll do the sulfate side first. So sulfate will be the oxidized form. We're probably going to need some amount of H+ and some amount of electrons. And the reduced form HS- on the right. And here we'll need 4 waters to account for the oxygens. Okay, that means we need 8 plus 1, so 9 hydrogens over here, and enough electrons to counterbalance that back to a -1 charge total. So that should be 8 electrons. And if you've ever worked with hydrogen sulfide degradation or transformation, it holds pretty much true that for every 1 hydrogen sulfide or bisulfide molecule, you need 8 electrons. It's an 8 electron process to get there, whether it's chlorine or it doesn't really matter. So this is why we often will use sulfur-bearing compounds to quench chlorine, for example. Actually, the thiosulfate is a bit of a safer one. Hydrogen sulfide is pretty hazardous, but things like, let's say, sodium thiosulfate, which, you know, if we could add as Na2S2O3, that is often used if you need to remove the chlorine from water for like an aquarium, or after doing a disinfection step in wastewater or something like that before you discharge. Okay, and it's just because it takes up so much chlorine to do that for all the electrons, and it's a quick reaction. All right, and ultimately you're not yielding a lot of sulfur in all that process, so it's very convenient for that also. Okay, that's the first one. The next one will be the chlorine dioxide. So ClO2 is the oxidizing agent, and we can pretty much, we're almost always going to have some protons and electrons. And what we can say is this should be going to Cl-. Whenever we're doing some sort of reactive chlorine, chloride is typically the end product that now it has been reduced. All right, and then some amount of water. It should be 2 waters because we have 2 oxygens. All right, that means we need 4 protons and a total of 5 electrons to get it back to a 1-. All right, so now we have 5 electrons and 8 electrons, and there's not really a great way to simplify that, so we're just going to multiply everything by 8 and by 5. So kind of a big numbers here, but when we do it all, the bisulfide should have 5 of those, plus 8 chlorine dioxide molecules, 4 waters, will be in equilibrium with 5 sulfates, eight chlorides, and 13 protons. Okay, so adding a lot of acid when we do that reaction. Okay. All right, so that's about it. Any questions, concerns, thoughts on all that? Okay. Yeah. You'll get most of the credit that way. Yeah, if you're going along the proper steps. Yeah. Right. Okay. Whenever I finish grading them. Since there's not too many of you, I don't think it'll take me too long. So probably early next week, I would think. Mid to early next week. Yeah. If I graded your homeworks also. Did already, right? Not the MATLAB ones, the other homeworks. I think I did, right? Did I post it? Maybe I need to grade this if I didn't. Okay. Yeah, so next week I'll be catching up on grading and doing more grading, basically. Okay. Last time we talked about photochemical reactions, and I realized, kind of looking back over it, I probably ought to give you a little more insight into the particular radicals that we might expect. So we talked first about what does this photochemical system look like? How do we describe it with an energy diagram? What are the common routes for things to take? We talked a little bit about direct versus indirect and other indirect processes that can degrade, destroy molecules, transform stuff. Sometimes there are some chemical synthesis routes that use photochemistry. So it's not all just destruction. Maybe we want something in particular to happen and can use something to produce a chemical. But at any rate, the direct photolysis, that's when a molecule, when it gets absorbs a photon, it directly splits apart. Indirect photolysis would be cases where we produce some reactive intermediate, and then that goes and causes some lysis of a molecule, or maybe it's not even a photolysis necessarily. It could just be some change or destruction or whatever, oxidation event, reduction event. Some event occurs. So those are kind of lumped in with this indirect photolysis or perhaps some other category. Okay, so we talked about the DNA as kind of the direct damage that's not exactly photolysis, a little bit more of a synthesis reaction in a sense. And I wanted to comment a little further on direct photolysis itself. So it's really a very straightforward process if we are thinking about it from a kinetic standpoint. How fast is it going to happen? What's going on? Given that the fundamental photochemical laws are that each photon absorbed is going to give us one product. That's kind of the two of them combined. That means that we're going to be pretty much having a first order reaction given some light intensity, some dosage, with respect to how much of that molecule that's doing the absorbing is present. So when we have a lot of it and sufficient light, maybe we're I don't know, destroying 10% per minute. That's a lot of molecules, but when we have a little, 10% is not so much, and so that, you know, first order properties we expect. So if we think about like what might be examples, most of our UV-driven advanced oxidation processes, or AOPs, are going to be directly photolyzing some oxidant so that we can generate more highly reactive species, these radicals or these intermediate products that are going to go and do the action for this advanced oxidation. It's certainly not limited to just these molecules. We might have some organic molecule floating around in the water under the sunlight and absorbs a photon and falls apart. Right? That can certainly happen as well. So these are good examples because they're just pretty straightforward. So we talked a little bit about hydrogen peroxide. We can get two hydroxyl radicals by direct photolysis. Ozone also can split into molecular oxygen and an oxygen singlet. Now, this is not singlet oxygen. So quite confusing, but it's just an oxygen atom. It's going to be a radical in that form, and it'll quickly react with something else to form some other molecule. So it's an intermediate species. We can also do direct photolysis on chlorine to split HOCl apart or OCl minus apart. I've got a slide showing some more of those, but ultimately we can potentially get chloride or chlorine radicals, Cl dot and Cl2 dot. Are potential radicals that we can form that are going to act a little different than some of these oxygen ones. Okay, so we talked, and I drew up this slide. I didn't have text on it at the time, but I said these PPRIs photochemically produce reactive intermediates. I described these as like when we have the organic matter becoming reactive, and that's the intermediate. Technically, I guess we can include any radical that we form as a photochemically produced reactive intermediate. But a lot of times in the scientific literature, people will talk about ROS, the reactive oxygen species. And then they'll say, oh, also other PPRIs. So a lot of times it's like this organic matter side of things is what, at least in the literature, is described often as the PPRI stuff. So depending on how you say it, it could be all of it. Regardless, I felt like maybe I ought to come back to ROS a bit further and describe a few of the more common ones, more important ones, with a little more detail. But PPRIs, if we are holistic with it, it'll be those reactive oxygen species, or in the case of something like the chlorine photolysis, or perhaps in seawater where we have a lot of halides, maybe we'll say that would be RHS as well, so reactive halogen. So a chlorine radical is not oxygen, so it's not an ROS. It'd be an RHS or RCS or something. So yeah, and I guess those would be categorized with the others. And there are quite a few that other species that can take the radical and persist for some time, and that may be a way to measure them, as we'll see, or perhaps just carry the radical around for a little while. All right, so we talked about the photosensitization. This is one way we get some of the radicals. In this particular case, this is single oxygen, which is not technically a radical, or maybe you can even just say oxygen in general is a diradical, which is a weirdo. However you want to look at it, this is not typically classified as a radical because it does not have an unpaired electron, but oxygen is a kind of a weird animal, and single oxygen is just a bit more reactive and does not live for a long time, doesn't have a long lifetime in water. But the point is, we looked at one way where we can do that photoexcitation, and instead of yielding some photons, we yield some reaction that's producing a reactant that we might could use for disinfection or degrading chemicals. Okay. Next, we came to photocatalysis, which is a similar procedure in terms of excitation by light. Something happens with the electrons, and we produce something reactive. But on a technical sense, the chemistry is a good bit different, and I think we didn't really cover it too much. So when we hit a photocatalyst with light, we end up separating an electron and a hole. So in this case, instead of exciting an electron, and the electron within the molecule is just simply now in a different orbital, it's like in an excited state where it's a little higher energy, ready to react with something. Now we are kicking it out, and these are usually often solid materials, and so there's physical space for these to travel. So now we have an electron that's what we call into the conduction band. I think I've got this. And the hole remains in that valence band, and the electron can move to the surface of the material and go and react with something. The hole left behind is also quite reactive and will be another source of radicals. So I'm oversimplifying a bit here, but essentially the electron can reduce oxygen to a superoxide radical anion, O2 dot minus. Now, this thing can go through various reactions, can get us to OH radicals, also to hydrogen peroxide. There's a lot of intermediates involved, so superoxide radical anion is an intermediate all by itself. So there's going to be various pathways and various things happening, and it's not just that this is the only thing that's there at all or anything like that. On the other hand, the holes can take hydroxide, OH minus, and oxidize that, take away that electron, and give us the hydroxyl radical. So those are the photocatalysts then are pretty good at forming hydroxyl radicals at the surface. Okay, so there's a few reactions written up here, and we can also take a look at some quantum yields and things like that for a few different molecules that maybe we can degrade with a given TiO2 system using different lights and different things like that. Okay, so what is a hydroxyl radical? Talked about it a lot by now. This is known in the atmospheric chemistry field as the atmospheric cleansing agent. It is an extremely reactive radical. I think there's very, very few that would be more reactive, maybe some of the fluorine stuff. But it essentially is really, really interested in oxidizing something. It would really like to be back to OH minus, essentially, and satisfy that. So it is extremely short-lived because it's just going to react with almost anything. It'll find a way to react with water. It'll react with other hydroxyl radicals. It'll react with organic matter. It'll just react. Okay. So when we look at the kinetics, typically the the kinetics for radical lifetimes are essentially second order. So they really are not going to stay around very long. So what we do is we estimate some steady state concentration. And what is that exactly? Before we move on, we'll say this pseudo steady state concentration. Essentially, we can find that in a system where a radical is being produced by measuring the effective amount that's there, watching something else decay, or maybe watching something else be produced in a system. So rather than try to detect the hydroxyl radical itself, which is going to be very difficult if it's only hanging around for less than a nanosecond, rather than try to find a way to measure it directly or to let enough of it accumulate, we end up estimating it because it's almost instantly produced when it is produced, and it's almost instantly removed when it is removed. So we can estimate it by watching some sort of reaction happen, and then in doing so, we get typical measurements in natural waters. Might be a stream, river, lake, ocean. They range from 10 to the minus 15 to 10 to the minus 18 moles per liter as a steady state concentration. Now, I've worked with some systems with photocatalysts in a batch reactor with tons of catalysts and really bright light, and we might estimate something like 10 to the minus 8th or 7th moles per liter. That's interesting. We might have no more projector here. It's working on my computer. All right. Well, I'll just talk at you for another 5 minutes, and then we'll call it a day. Okay, so hydroxyl radicals, they disappear so quickly, and maybe I'll use some chalk if I feel like it. They disappear so quickly that mostly what we can do is simply get an estimate there of how much is there, and that's kind of the best we can do. They can be generated a few different ways. Nitrate can go through some photolysis. It's not very efficient in it, but you can get a little bit of hydroxyls from it. Natural organic matter, we talked about that, kind of doing that photosensitization thing. If there's an electron transfer, like an oxidation or reduction involved with that excitation, sometimes you get some of that superoxide radical anion, which can get us to hydroxyl. We can also form a little bit of hydrogen peroxide, which can then be photolyzed. So hydrogen peroxide, turns out, which was the next one I was going to talk about, or one of the next, is also a little bit naturally occurring. Next on my list, and I'll post these slides so you can see them later, was singlet oxygen. We actually talked a fair bit about it. That's the 1O2. Singlet oxygen like that. Already glad I don't use the chalkboard. So that's the squeak alone. Maybe I'll arrange this so that any viewing later, you'll see it anyway. So single oxygen, it is longer lived. So if a hydroxyl radical lives for maybe a nanosecond, this is 1,000 times longer lived, so maybe a microsecond or a 5. But it doesn't last very long. If you do an experiment with heavy water, so deuterated, so that you have each H has a neutron and a proton instead of just a proton, that actually makes it last about 10 times longer. So it's kind of neat. You can tell if you have some reaction. Well, we don't know if it's single oxygen, do the same reaction in deuterated water, which is quite expensive. And your amount of single oxygen goes up by about an order of magnitude. That's probably single oxygen involved. So it's kind of neat. It's really effective at destroying viruses if you if you've got them next to it. So we've done some experiments like that. We also find it naturally occurring in water, a bit higher concentrations than hydroxyl radicals because it lives longer and it's just a little easier for the organic matter to produce it. I think it's 10 to the minus 13 is probably a typical range for that one. I don't have the exact number, but that's in my mind. Hydrogen peroxide, you know a fair bit about it, and I can't show you a fun video on that. But in the store, you can buy a bottle of it, and it's like 1 to 3%, somewhere around there. Of course, we don't have nearly that much in nature. If you've ever poured hydrogen peroxide over a little cut, essentially what you're doing is something I was going to mention. It's Photochemistry. It's related to photochemistry because the iron can also do some photochemistry, but essentially what you get when you have iron and peroxide is it's catalytically splitting the peroxide into hydroxyl radicals. So when you pour that on your cut with a little bit of blood on it, if you had no blood, there would be no reaction. But since there's blood, you get fizzing because the blood has iron in it, right? The chelated iron. And so that's catalytically causing the peroxide to split apart, and you're releasing some oxygen gas in that, and it's just a highly reactive area. So you don't want to like overdo it, right? You want to do it enough so that whatever bacteria might be there, viruses, are probably going to be just destroyed, but there's would be no good thing would happen if you just like left it there for an hour, like dunked in peroxide, because then as soon as blood comes out, it's going to burn your skin eventually, or your stuff. You just want a little bit of burn. Okay, so peroxide, you kind of are aware that it has some potential use. It lasts for a long time, and we have, I think, millimolar or micromolar concentrations of it in a lot of natural systems. We use it as an advanced oxidation process, so we can split it directly. That's another relevant aquatic chemistry thing. Sometimes we'll add acetic acid, so vinegar, and we get a mixture that is part peroxide and part vinegar. That's peracetic acid. It's another disinfectant. Kind of a new one that's being used for wastewater disinfection. That's not really photochemically active in most systems, although I think with a low wavelength UV lamp, you could probably photolyze, well, you can at least photolyze the peroxide, but probably the acetic acid too. Okay, so you can oxidize some things with hydrogen peroxide. It's probably a stronger oxidant than oxygen, but a lot of things will just kind of ignore it. Okay, then I had some lists of common photoreactions just to see how they're shaped. And I was going to tell you a little bit about chlorine photolysis in particular. It's a research topic. And some tools and strategies of how do we detect these radicals if they're so short-lived. There's kind of three main ways to do it. One would be actually using something that can go that fast, which takes some really fancy lasers. And it's called laser flash photolysis. You're actually going to do this a bunch of times in a very short sequence, but you're going to pulse a light, excite your molecule, and then have another light that's coming from the other direction to check your UV visit absorption. And that just has to be really, really fast, and then you can see how much light the radical or the intermediate species is absorbing. So it's really cool. A fair amount of labs around the world can do it with these fancy laser systems, but it does take a lot of specialization. So anytime you try to work with a fancy lab like that, they're like, I've already got too many projects. No. It's the typical response. Okay. The other thing, and I kind of mentioned this already, is to observe the kinetics of something. And so if we're dealing with first order kinetics, then we can watch the decay or the production of something. Often we'll take the decay, and if we plot it on a natural log plot versus time, so natural log of the concentration of something over time, we can very simply track the kinetics there of the thing degrading and figure out that K is going to be related to the concentration of our radical, so, or rather this steady state concentration of the radical times some rate constant or some factor to deal with. Let's see. I'm just going to say this is relates to it. There's some other factors there, right? So maybe we'd say this is K star, and that has a specific rate constant involved with that reaction. So I'll just write it here. I'm just going to write this also on here for later. Okay, so that's one way to do it, and we just simply need a probe that is sufficient to do that type of reaction, that we have some known amount, known rate constant for that reaction together, and we can do that. We probably also need to add in the concentration of the thing here. Or no, that's accounted for. Okay, so that's kind of the second way, and you can do that with maybe measuring some product that's forming, measuring something that's being degraded. Another way is very similar. It's just kind of a different way to measure the product in a sense, is electron spin resonance or electron paramagnetic resonance spectroscopy. And that's a fancy way to make use of the fact that the electrons are in a particular spin arrangement. And when we have a radical, if we react a radical with a molecule that can trap that spin, meaning stabilize the radical so it doesn't react with anything else, at least for several minutes. A few molecules can do that, have the long-lived radicals. Then we can use this fancy, it's like an NMR, where that's nuclear magnetic resonance. You're causing the nucleus of an atom to, with a strong magnetic field, you're causing it to orient based on its poles. You can do that with a less strong magnet for the electrons, because those are easier to manipulate, and then use a microwave to find that signal. So it's a fancy looking squiggly line, looks pretty cool. Kind of like that, maybe with some more texture depending on what it looks like. But you get a neat signal that you can work with and go from there. Okay. I think that's probably about it. So with that, I'll say good luck on your projects, and see you guys later.